Hi, we are the humic acid subteam. My name is Matt.
My name's Carolyn.
So some background on humic acid in general and about our subteam is, well, first, humic acid, for those of you who do not know, is present in nature around us. It composes a lot of the natural organic matter that is in leaves and trees and all that good stuff. And so when humic acid in the leaf, let's say a tree leaf, gets into water, it can actually dissolve in water. And so humic acid in water can produce many harmful effects, especially when we try to treat water with, for instance, chlorination. Chlorination can produce very harmful effects if humic acid is present in the drinking water. And humic acid itself is a very sticky substance. So if we try to treat water with coagulant, for instance, the coagulant can be coated with humic acid, making it harder for flocks to form because it's harder for all the molecules, coagulant molecules, to stick together and collide. And so previously, the humic acid subteam was established in fall 2017, and mainly in the fall 2017 and spring 2018 semester. The humic acid subteam did a lot of research into what is the optimal coagulant dosage that we can add into a water stream with humic acid that will take out or essentially filter out a lot of the humic acid that is in the water. And so what they found was that for a concentration of humic acid that is 5 milligrams per liter, the optimal coagulant dosage is between 1.6 to 1.8 milligrams per liter. And then for 10 milligrams per liter of humic acid, the optimal coagulant dosage is 1.3. And so at the conclusion of the spring 2018 semester, the humic acid subteam felt that no further research into the optimal coagulant dosage was needed for the different amounts or different concentrations of humic acid, because as you can see on the chart on the right, on the plot on the right, it is a plot of effluent turbidity versus time fraction at 5 milligrams per liter of humic acid. But you can see that for various coagulant dosages, you see that between like 1.3 to 1.8 milligrams per liter, after a certain amount of time, the effluent turbidity decays to the same value of about 0. So we felt that the spring 2018 humic acid subteam felt that further research was not needed, because once you hit into this sweet spot of coagulant dosage, after a certain time, the effluent turbidity decays to 0. And so in the fall 2018, the humic acid subteam got a spectrophotometer, and so there was a lot of toying around with how we can use absorbance to quantify the amount of humic acid in our system, and how we can try to use that to see, maybe measure the efficiency of how our water treatments are doing in the removal of humic acid.
So this is our new experimental design. Before we had all the pumps and all the meters, and we were using water from the tap water system. Now we've taken out the 2 pumps at the top, and we've taken out the effluent turbidimeter. Our new system is, this is a schematic drawing. Basically we have the 6 liters of water in the water bucket, and then we have a water pump, and then it goes through the turbidimeter, the spectrophotometer, and back into the 6-liter water bucket. And with this experiment, this design, we first verified the absorbance result we had of clay, different concentrations of clay and humic acid from last year's results. So we tried to see if those were the same, and then the next thing we did was we put clay and humic acid together, and then we tried to see what the absorbance of the mixture would be. So first of all, before we put them together, we added their respective absorbances together, and that's on the right side of the column. That was the projected absorbance. That was just adding them, and then the actual absorbance is the number that shows up on the spectrophotometer. So this is our experiment number 1 with 5 milligram per liter humic acid and different concentrations of clay at 10 NTU, 100 NTU, and 1000 NTU. And then this is our second, which is at 10 milligrams per liter, and then our third at 15 milligrams per liter. So as you can see on all of these 3, for the last row, the actual absorbance was maxed out at 2. We think that this is because the concentrations of both clay and humic acid were so high, so that the meter could not give us a accurate number, so it just maxed out at 2. And then here is the, basically we just calculated the percentage difference of the projected absorbance to the measured absorbance. And as you can see, at the smaller concentrations, the percentage difference is actually pretty much within the 20% range, but then at higher concentrations, it was pretty off. But it might be just because the meter is giving us the number 2 for the absorbance. Yeah.
And so after doing all this experimentation and all this data collection, we decided that it would be best to compile this data into one graph. And so we made a plot of the ratio between measured and over predicted absorbance versus the measured turbidity. And so in doing so, we hope to see how our the actual observed absorbance compared with the predicted absorbance of just adding the absorbance of humic acid with the absorbance of the amount of clay that was in the system. And so as you can see on the plot, all of the with the exception of one trial, all of the data, the ratio between the measured and the predicted absorbance was below 1. So this means that our measured absorbances were lower than our predicted model. And so this is telling us that we need to find a better model rather than just adding the absorbance of humic acid and absorbance of clay, because that model is not giving us an accurate reading of what we're actually observing in real life. And some of the complications that we ran into during our testing was that, well, first when we ran our experiments, we first, through the recycle system, we first ran just distilled water through the system, and we noticed that on certain days the absorbance of the distilled water would be much higher than other days. So there were some complications in, some confusion, I guess, or complications in using, like, we got this data, but the absorbances are much higher than the other trials because the absorbance of the distilled water that day was much higher than the others. And so that was one of the complications we ran during experimentation. And another is that after we started running a couple of trials, and then over time we found that there was some minor amounts of clay that were stuck to the tubing. So we had to fix that, but that could have impacted our absorbance readings. And there was also algae because our tubing was kind of green, and that also could have affected our measurements. But after we found that out there was algae, we made sure to consistently bleach our tubing whenever we found algae in the tubes. And then some future tasks, looking ahead, as I talked about a bit earlier, you know that there is some discrepancy between the measured absorbance and the predicted absorbance model we have right now. So we want to see if there's some correction term that we can derive from our turbidity measurements that will help correct our model to make a better model that will predict a much more accurate absorbance that we will be able to read off of the spectrophotometer. That's all for our presentation. Thank you guys for listening.
Thank you.
If you guys want to do any more research into humic acid, you guys can check out our appendix slides, or you can head over to our GitHub and check that out as well. Thank you.